Yeah, so I'll be quick in just introducing this. So we're going to have these 3 keynote talks, which are going to give an overview on each of the big picture questions that we want to discuss that Ari introduced at the beginning of the workshop. And first up, we're going to have another tag team situation between Penny Wieser and Shuo Echo Ding, talking about the gaps in our knowledge and experimental issues and modeling issues in addressing those gaps.
Okay, can you see the slides all right?
We can.
Yeah. Okay, so I'll get started. So yeah, this is a team effort of things we've compiled together. So we found a few gaps when we were writing the VSeCal2 paper, specifically for water and CO2 solubility. So I'm going to talk about that and then pass over to Echo for sulfur. So the first thing we noticed is that there's a lot of discrepancies in how the models deal with redox. And this came up in some of the talks earlier. So specifically the ratio of iron 3+ to iron total. So Lu for rhyolites doesn't have a melt composition term, so it doesn't matter. Volatile calc for basalt and rhyolite either uses silica or doesn't have a melt composition term, so that also doesn't matter. Yacona Marciano and Moore specifically use iron total to get around these problems, so those models have no sensitivity to redox. The Shishkina model does have a term for the Fe2+ in the melt, but interestingly, they actually calibrate the model with Fe total. And that is because they say that of their 48 experiments, only 7 had any constraint on the amount of Fe3+. So they decided it would introduce less error to not try and parameterize it. So when you're using this model, you might also want to use Fe total because that is how it was calibrated. The interesting ones are Papale and magmasat. They have interaction parameters which are kind of describing how the melt composition affects solubility for both iron and Fe2O3. And the really interesting one for this is Papale's model from 2006. This is extremely redox sensitive. And you can see this by looking at the coefficients for the Fe2O3 and the FeO term. So if we look at this W0 coefficient, for example, we see that it is 200 times larger for Fe3+ than for Fe2. So this suggests that Fe3+ has a vastly different impact on CO2 solubility than total. But you can see the error on this FeO coefficient is enormous. The 1 sigma error is 806%. And similarly for this W1 parameter, the error is 1,500%. And the real problem with trying to build models which account for redox is we don't have the experimental data. So of their data set, 6 experiments out of about 100 know the Fe3+ ratio. 9 more know the FO2, and the rest had to calculate an FO2 value based on the H2O-H2 equilibrium. This can be influenced by things like H loss, iron loss, and the presence of CO2 in the melt. And this leads to some very interesting values in the calibration data set. So for example, for Vogel and Rutherford, they allocated an Fe3+ ratio of 90% for this experiment. And yet they say, and Vogel and Rutherford say that they have CO species, which means it was quite reduced. And there's some other examples of experiments being allocated high Fe3+ ratios, and yet the authors indicate that they were pretty reducing. So this is definitely a problem we need to solve, and it makes a massive difference to your calculations. So just doing some more calculations, we are running models for the 3 sensitive models, so magmasat, Shishkina, and Papale, for 0% Fe3+ and 20% Fe3+, which is the dashed lines. You can see, fortunately, Shishkina and magmasat, it really isn't that big a deal. It does not make that much difference. But for Papale, it makes a huge difference. You would almost double your solubility of CO2 just in a morb, depending on what redox state you choose. That situation is even more extreme if you look at, say, Etna. Some experiments on Etna composition were done with 60% Fe3+. And you can see here at a kilobar, having 0% versus 60% Fe3+, this is a change in CO2 solubility of almost 20 times. So this is something, obviously there are discrepancies in how these models are handling it. And that's simply because we do not have sufficient experimental data to really know how that FeO or that Fe2O3 term is influencing volatile solubility. There are then other concerns. So this is a helpful diagram from Kayla. So you can basically see that as you go change your oxidation state, you change your C species from carbonate to molecular CO2, and then all the way down to CH4 as well. So we also need more experiments if we want to look at other planets that are parameterizing that. The second uncertainty that we found was how models deal with mixed fluids. So for example, this is showing a morph composition, and this isn't a problem at low pressure. So all of these lines, the solid lines are at 1 kilobar, they're kind of similar. Once you get up to 4 kilobar, you can see these isobars show drastically different shapes. So while the pure CO2 solubility of volatile calc, Marciano, and magmasat are very similar, and while the pure water solubility of these are very similar, once you get in the middle of this space, you can change the amount of CO2 you have dissolved by a factor of 2, just based on the shapes of these curves. So you can see Marciano shows this really big hump up to high CO2. Papale shows this completely opposite sigmoidal shape. And then volatile calc is not dealing with non-ideality, which is why you have that nice declining slope. So why are we disagreeing on this? Well, it's because experimentally we're disagreeing as well. So here are some experiments. You can see on the left-hand side, we have King and Holloway. And you can see from these blue sort of diamonds that as we are increasing water, CO2 solubility is obviously going up. And we've just overlain the isobars from different models. So you can see magmasat is predicting this, and Papale is predicting this slope as well. But in contrast, the Borcharnikov experiments at 5 kilobars, as you increase water solubility, CO2 solubility is staying almost completely constant. So again, there are lots of discrepancies about what is actually happening. How much are we actually increasing CO2 solubility as we dissolve water? The reason this is so hard to work out is we just don't have very many experiments where the fluid composition is measured. And that's what we really need to build a robust thermodynamic framework of how this changes. So for example, one way you would do this is using a mammometry setup, a bit like this, where you would have to pierce your experimental capsule and release the fluid. There just are not very many labs that do this, and it is very, very challenging to do. So this is a serious thing we need to address in future. Another problem is water and CO2 non-ideality is bad enough. We know we realistically have sulfur and chlorine as well. And Borcharnikov say predicting fluid saturation based on water and CO2 only may not be completely correct. There is experimental work from Webster, say, in haplogranite systems of how chlorine solubility affects water solubility. And then there's some more recent experiments from 2015. And what you can see is the effect on water solubility based on chlorine, it's highly dependent on the pressure. There's a lot of uncertainty here, and we barely have enough experiments to say parameterize how CO2 is affected by melt composition, let alone doing it in this 4-component system. Then the final thing which we spotted as sort of a gap was we have a shortage of andesite and dacite experiments. So this is showing for pure CO2 and mixed fluids in TAS space where the different experiments are. You can see we have a lot of basalts, we have quite a lot of rhyolites, and we have quite a lot of high alkaline samples. What we do not have a lot of is dacites and andesites. And yet these are some of the most hazardous volcanoes we have on this planet. And if we're calculating melting fusion saturation pressures or degassing paths, we really want to make sure that these models are working. So to kind of test how bad this was, we took some experiments in the literature from andesite and dacitic compositions, and we ran all of the models to try and see which behaved best. So for example, for Borcharnikov's experiments at 2 and 5 kilobars, you can see Papale does a pretty good job. It passes through the data, but these experiments were done with Fe3+ ratios between about 0.2 and 0.7. If we actually put that into the model, we end up with this dashed dot line, which is well below. The only way we can reproduce these experiments is running Papale at 0% Fe3+. Magmasat is a bit low, Marciano is kind of low, and Shishkina is kind of very, very low. On the right-hand side, again, Papale does all right, but only with no Fe3+. And some of these models, like volatile calc, for example, are really under-predicting volatile solubility. And then we can look at other experiments, and we see on the left-hand side here, magmasat, which is gray, and Papale, which is green, do okay. But on the right-hand side, the King experiments, Papali is suddenly very, very wrong. It's predicting extremely high volatile solubility. So what we find in general is that magnesat overall, while it doesn't behave the best for each experiment, it behaves the best in general. It's never more than 20 or 30% out. So you would never get a catastrophic result. But we still need far more work on this. We want to make sure that these calculations are right. And experimentally, this is challenging because in basalts, we mostly have carbonate species. And in rhyolites, we mostly have molecular CO2 dissolved. But in these intermediate compositions, we have both species in almost equal abundances. And to build a truly thermodynamic model, we need to quantify the relative abundance of these species. And that really is the framework we need to have these thermodynamic models consistently reproduce andesite and dacitic experiments. So that's CO2. I'm going to pass on to Echo now for sulfur.
All right, thanks, Penny. So in the following a few slides, I'm going to talk about some of the potential experimental gaps in terms of modeling sulfur degassing in basalts and basaltic andesite system. So the first experimental gap comes from the sensitivity of sulfur to redox conditions. As I mentioned before, sulfur can exist in the melt as both sulfide and sulfate, and this transitioning FO2 range is actually encountered by most arc magmas. However, there seems to be a lack of consensus of how sulfur speciation change as a function of FO2 calculated by different models. So these three colorful range, like yellow, pink, and bright orange, are calculated sulfur speciation as a function of FO2 by three different models in the same temperature range between 1000 degree to 1300 Celsius degree. So the right side boundary is the lower temperature, and the left side boundary is the higher temperature. So we can see that depending on what temperature we're looking at, these three models can actually predict pretty different sulfur speciation in this intermediate FO2 range, which would actually affect the impact the underneath sulfur degassing degassing mechanism here. So among these three models, the Muth and Wallace model is actually an empirical fit of melt inclusion data from cascades, where the authors actually measured sulfur and iron speciation in the melt. And the other two models are calibrated based on one atmosphere experiments. So Nash model is purely a function of ferric iron ratio and temperature. And it shows a really large temperature effect. And the O'Neill and Mavrogin's model shows that it's a function of ferric iron ratio, temperature, as well as melt composition. So both models are calibrated using experiments at 1 atmosphere, and all the experiments are dry. However, when we look at like arc magmas, they are usually at greater depths and contain some water. So what we really need is a systematic experimental constraints to constrain sulfur ion speciation change as a function of FO2 at pressure higher than 1 atmosphere with water, and ideally with a different melt composition. For example, iron concentration is likely to matter, and more important, all the experimental products needs to be measured for sulfur and iron speciation to calibrate the models. So these sets of experiments would not only be useful to calculate sulfur speciation in the melt in order to understand sulfur degassing, it can be also very useful to calibrate, for example, sulfide and sulfate capacity, which a couple of speakers have mentioned before at high pressure, and also to use to calculate how sulfide saturation value actually change as a function of FO2 in the magmas with a mix of sulfide and sulfate species. Next slide, please. Actually, 2 slides. Next one. Thanks. Okay, so the second experiment gap I want to talk about is there's a lack of experiments at pressure between 500 megapascal and 1 GPa. as people started to take CO2 in the vapor bubble into account, the pressure where magmas start degassing has also been significantly increased. For example, the rehomogenized multi-inclusion data set from Fuego is a really good example showing that sulfur could actually start degassing much early at pressure higher than 500 megapascal. However, regardless of FO2, all existing experiments for basalts and basaltic andesites publishing data are all under 500 megapascal. So even within, so this is not only about to fill the gap between the pressure of 500 megapascal and 1 gigapascal, but also because at high pressure, the vapor would be more dominated by CO2, and we cannot extrapolating the lower pressure experiments, where the vapor phase is more dominated by water, to higher pressure. Basically, we are assuming that sulfur behaves the same when partitioning into the vapor phase, where water is dominant and the CO2 is dominant. So we do need more pressure, more experiments at higher pressure, and ideally with a mixed fluid of water, CO2, and sulfur to constrain sulfur behavior there. So even within this lower pressure and temperature, lower pressure range, for the existing experiments, we can also spot some gaps and issues here. So for example, this figure shows experiments for sulfur partitioning experiments for reduced condition shown in filled circles and oxidized condition shown in open diamonds. So we can see that for reduced experiments, they are really limited to pressures lower than 300 megapascal and very low temperature. And this is related to one of the experimental challenge I will talk about later. And next slide, please. And for the oxidized experiments here, we can see that they actually covered a wider composition variation as well as the pressure and temperature range. However, most experiments are still below 200 megapascal here, and the only experimental study at 500 megapascal are actually conducted with very extreme melt composition here, which they are also the sets of experiments Ewan pointed out earlier, that they have very low partition coefficients for sulfur. So it's not very clear here whether this low sulfur partition coefficient from these experiments is due to the pressure effects or is due to this very high alkaline composition here. Next slide, please. And then this figure shows the experiments at intermediate FO2, and they're more likely to suffer from many experimental challenges when we want to do experiments on sulfur. For example, some of them suffered from sulfur loss to the capsule, to the noble metal capsule. And some of them, the FO2 was either underestimated and also suffer from hydrogen loss. Next slide, please. So there's another set of experiments at intermediate FO2, which actually showed significant sulfur alloy with the capsule. Next slide, please. So now this naturally leads to some of the experimental challenges when we are dealing with sulfur in the lab. So first of all is the choice of capsule. These are particularly important when we want to run experiments at intermediate FO2. So sulfur is notoriously known for reacting with many noble metal capsule, which is the choice to go when we want to run fluid saturated experiments. So for example, this offer panel is two figures from Gennaro et al. So they used a platinum capsule, and they actually show this show a layer of platinum iron sulfur alloy between the capsule and the silicon melt here. So these definitely significantly affect the sulfur budget here and cause overestimate of the sulfur partition coefficient here. So usually gold gold, and maybe gold enriched gold palladium would be the better choice to avoid this issue. However, because they're very low melting point, this actually limits the experimental temperature. This also kind of explains why most of the reduced sulfur experiments are actually at relatively low temperature here. There's some other choices, for example, using a downite or crushed olivine inner capsule. However, this also has its own issue. For example, this is an image from one of my own experimental charge. I used the crushed olivine inner capsule, and then this is my glass, and then the olivine, of course, reacts very severely with my with the silicated melt, and also because even though I sintered olivine capsule overnight, it seems it didn't successfully contain sulfide melt. So many of the sulfide blobs actually were disseminated in this olivine capsule. So the second issue of doing this kind of experiments is to avoid sulfur-bearing solid phases like sulfide or anhydride in the experimental charges, because this solid phase can take a lot of sulfur, causing an overestimate of your partition coefficient. However, they are very difficult to quantify. So one of the solutions to here would be, as Penny just mentioned, is to directly measure the fluid composition, which has its own issue. For example, how to extract a very small amount of fluid in the experiments, which we are usually talking about 10, 20 milligrams into the gas line. And the sulfur is a very corrosive gas, so one would need a dedicated gas line to measure these kind of experimental products.
Echo, we're getting a little long here, so you need to wrap up quickly.
Okay, so thanks. So I guess one last gap I would really like to mention is that there's a lack of experiments at low pressure between 1 atmosphere and a few hundred bars. So these sets of experiments can be really important to calibrate models that to predict the vapor phase to be compared to the volcanic gas data. So this figure actually shows that many experiments at 1 atmosphere actually has a orders of magnitude higher of partition coefficient compared to experiments at pressure. However, all these experiments, again, they're dry and they're in a gas atmosphere of SO2, CO2, and CO. And this is very different from a natural volcanic gas composition. So what we need is really more experiments with water-bearing experiments at near surface pressure to better calibrate the sulfur partition coefficient in this pressure range. Okay, thanks.